All right, welcome everybody. Today we're going to talk about lesson number 71. We are still in section 9.3, but instead of just talking about geometric sequences, we are going to start adding them up and turn them into geometric series. Now, there are more formulas to come today for finding the sums of geometric series. There are formulas for what to do if you're adding up a finite series and formulas for what if you're adding up an infinite series. So again, if you haven't been keeping track of all the formulas so far, you certainly do want to do that sooner rather than later because there are still many more formulas to come. So just a little reminder of what it means to be a geometric sequence. The ratios of consecutive terms has to be the same. So if you divided any term by the previous term, you always have to get that same common ratio R. Here is yet another formula for you to add to your running list. Hopefully you've been keeping a list of all the Chapter 9 formulas so far. You should also be noting whether or not the formulas have to start at 1, whether or not they can start at a different value, and then any compensations you might have to make along the way. So this formula here for the finite geometric sequence says if you are trying to find the sum of the first n terms, so long as you are starting from 1 to n, and as long as you have a geometric sequence, then you are going to put the first term out front. You are then going to have a quotient where the numerator is 1 minus the common ratio to n divided by the denominator, which is 1 minus r. So as always, plugging stuff into this formula is actually quite simple. It's just a matter of plugging it into your calculator and ensuring that you get the right answer. That can be a little bit more challenging. So take, for example, here, number 1, you are trying to find the sum from 1 to 12 of this geometric sequence. First of all, a couple things to notice. You know that it's finite because you know where it's starting 1 and where it's ending 12. And then the fact that the equation looks exponential is how you know that it's geometric. If you want to start, go ahead and plug in the first couple of values from 1 to 12. If you plug in 1, you get this. If you plug in 2, you get this. And basically, you would plug in all the values up to 12 and then add them together. As a little bit of a time saver, we're going to use this new formula. So the formula is only good if you're starting at 1. So if you're going from 1 to 12, you are adding up a total of 12 things. The common ratio is always what is being raised to an exponent, basically the base. This A1 is what you get when you plug 1 into this equation. So when you plug 1 into this equation, 1 minus 1 is 0. 0.3 to the 0 is 1. 1 times 4 is 4, which is why this value out front is 4. The common ratio is the base of the exponential, which would be 0.3. And then because you're adding up the first 12 terms, it's why your exponent is equal to 12. So again, substituting in these values, I think is relatively simple to do. To ensure that you do in fact get the correct answer, here's my advice for how I would plug this entire equation into the calculator. I would start with the numerator by doing 1 minus parentheses 0.3 to the 12th. That's going to give you an answer, which I would just leave right in the calculator. Then divided by parentheses, 1 minus 0.3. Only once you've done that entire quotient should you then multiply it by the first term, which is 4, giving you a final sum of 5.714. And you can continue to round to 3 decimal places unless it specifies otherwise. Consider number 2, which is very similar to example 1, except now in your geometric sequence, it's only being raised to the I as opposed to being raised to the I minus 1. Notice that that's completely fine. The first couple terms of this series are a little bit different. You would again start by plugging in 1, 2, 3, etc., but you're going to get slightly different terms, including a slightly different first term. Your common ratio is always the base of the exponential. And then because you're still going from 1 to 12, you're adding up 12 things. So notice how the formula is almost exactly the same, except the first term is different because there was a slight differentiation here with the exponent. Again, if I was going to plug this into the calculator, I would start with the numerator, 1 minus 0.3 to the 12th. I would then hit divided by parentheses 1 minus 0.3, hit enter again. Multiply that whole thing times whatever 4 times 0.3 is, and then you're going to get a smaller sum of 1.714. Let's go ahead and do some examples from start to finish. So let's say you're being asked to add the sum from 1 to 7 of 2 to the n minus 1. The first thing you're going to notice here is that you are finding the sum of 7 terms. So you're going to go ahead and start by finding the first term, which is what you get when you plug 1 in for n. That's going to give you 2 to the 0. Anything to the 0 is 1. Then you have a fraction. The numerator of that fraction is 1 minus the common ratio, which is 2 raised to the 7th, divided by 1 minus 2. And again, I think plugging those numbers into the formula is quite simple. When you now go to plug this into your calculator, I would do the numerator first, divided by the denominator in parentheses, multiply that answer by 1, and that is going to give you a sum of 127. If you wanted to verify that that answer was right, you could plug in all the values of n, 1, 2, 3, 4, 5, 6, 7, into this formula, add them up, and I promise you'll get the same answer. Example 4, take a look. Again, because it looks exponential, that's how you know that it is in fact a geometric sequence. You're adding up the terms from 1 to 20, which means you're adding up 20 things. The first term is what you get when you plug a 1 in for n. So again, 1 minus 1 is 0. Anything to the 0 is 1. 1 times 10 is 10. In the numerator, 1 minus the common ratio, which is 1/5 to the 20th, all divided by 1 minus 1/5. Again, be extra careful when you plug this into your calculator, but if you do it correctly, you should get a sum of positive 12.5. Here in example 5, notice this is the first example today where you're starting at 0 instead of starting at 1. Turns out that that is an issue for the formula because according to the formula, you do have to start at 1. It doesn't mean that the problem can't be done. It means we have to make a slight compensation. Basically, in the past, when we tried to use the formulas, we had too much and we had to subtract. Now, based on the formula, we have too little, which means we have to actually add something in. If the formula is only good from 1 to n, and we're going from 0 to n, you actually have to start by finding whatever the 0th term is. Then you're going to add the sum of the terms from 1 to 40. So for the sum of a finite geometric sequence, this is the procedure you'll always have to follow if you're starting at 0 as to opposed to starting at 1. And you're never going to see any other examples except starting at 0 or starting at 1. So a sub 0 means what you get when you plug in 0. So if you plug in 0, you get 3/5 to the 0, which is 1, times 5 is 5. Then from 1 to 40, you are adding up 40 things. So you are going to start by finding what you get when you plug in 1. 3/5 to the first is 3/5, times 5 is 3. So 1 minus the common ratio, which is 3/5 to the 40th, divided by 1 minus 3/5. So go ahead and calculate this entire sum separately using the procedure that I showed you in the previous examples. Then add 5, and that is going to give you a total sum of 12.5. Just FYI, for some reason in this chapter, an awful lot of answers wind up being 12.5. It's just kind of a coincidence, so don't think too much of it. Here in example 6, I want you to use summation notation to write out the sum. So the first thing you would realize here is that because the values in your sequence appear to be doubling, that implies that it's geometric. In order to know for sure, you would try to find R by calculating the ratio of any consecutive terms. Oh, sorry, this should be a 7. And if you go ahead and do that, you can conclude that R does in fact equal 2. So you're going to go ahead and write this as the sum. Unless the problem specifies otherwise, you're going to assume that you are always starting at the first term. So n equals 1. The formula for a geometric sequence is the first term times r to the n minus 1. What you then have to decide is what term in the sequence is 896. So once you deduce this formula, you could actually use a little bit of guessing and checking to figure out what term number that is. If you want to do it more formally, you would take your equation, 7 times 2 to the n minus 1. And I know you would never try to multiply 7 times 2 and get a 14. That's not a thing. And you would set it equal to 896. You could then go ahead and divide both sides by 7. So that would give you 2 to the n minus 1 is equal to 128. If you were to realize that 128 was equal to 2 to the 7th, you would then know that 2 to the n minus 1 equals 2 to the 7th. And as long as you have those like bases, you could go ahead and set those exponents equal, which would tell you that n was equal to 8. So your final answer to this problem is the sum from 1 to 8 of the geometric sequence 7 times 2 to the n minus 1. Similar problem here in number 7, so feel free to pause and try it. Here in number 7, assume this is the first, second, third, and then ultimately we have to decide what term number is it going up to. You're going to go ahead and try to find the common ratio by dividing any term by the previous term. Reducing will tell you that the common ratio is -1/5. Assuming you're starting at the first term, this is the sum from 1. In order to write the geometric sequence, you're going to start with the first term, which is 15. Then the common ratio, -1/5, raised to the n minus 1. And again, once you have this equation, you could either do a little bit of guessing and checking to figure out what term number -3/625 is, or you could set it equal to -3/625 and solve for n the same way that we did on the previous slide. The truth is it probably takes you approximately the same amount of time, and it turns out that -3/625 is the 6th term. So we've been talking a couple of times now about what it means to be finite. So perhaps you're wondering, how could you possibly find the sum of something that was infinite? If it goes on forever and ever, how is it possible that you could actually add all those things up? Well, it turns out that there is a way, but in order for that to happen, there has to be a very specific circumstance. So if you go back to 9.2, you'll notice that there was no formula for the sum of an infinite arithmetic sequence. That's not a thing. It only works for an infinite geometric sequence, which is called a series. And further, it only works if the absolute value of the common ratio is less than 1. So let's talk about why that is. Notice over here, this is the formula that we used for the couple of previous slides. That was for a finite geometric sequence. And now we're talking about what would happen if it's infinite. So if it's infinite, you're assuming that n is going to infinity. So consider what would happen to r to the n given specific values of r. So let's say that the absolute value of r was not less than 1. So let's say that r was 2. If you did 2 to the first, you'd get 2. 2 squared, you'd get 4. 2 to the 10th, getting bigger. 2 to the 20th, getting bigger and bigger and bigger. If your sequence is getting bigger and bigger and bigger, there is no way for you to find the sum because it just keeps going and going and going. Let's say instead, though, that the absolute value of r was less than 1. So let's say instead of 2, that it was 0.2. If you did 0.2 to the first, you would just get 0.2. Let's say you did 0.2 squared, you would get a smaller value. Let's say you did 0.2 to the 10th, getting even smaller, to the 100th, smaller again, to the 1000th, even smaller and smaller and smaller. So as this value of n is getting bigger and bigger and bigger, we would say going to infinity, the entire value of r to the n is getting closer and closer and closer to a value, which remember is called a limit. What value is it getting closer and closer to? Well, it's actually getting closer and closer to 0. So it essentially becomes 0, which means we eliminate it from our formula. Because of what we're left with here, we're simply going to distribute the a sub 1 to the top, which gives us our final formula for the day. So again, notice that this is only true for the sum of an infinite geometric series. And again, it's only true if the absolute value of r is less than 1. So you do have to check that. Notice that there are two formulas here, one if you're starting at 0 and one if you're starting at r. If you're adding up an infinite number of things, whether you start at 0 or whether you start at 1, turns out it actually doesn't matter, because if you're going to infinity, the difference of one term in each of your sums is practically negligible. So notice that when it starts at 0, you're going to have just r to the variable, whereas if it starts at 1, you're going to have r to the variable minus 1. Regardless, the formulas are the same. And the numerator of the formula is whatever you get when you plug in the bottom number, whether it's 0 or 1. So this formula is always where the series starts, whether it's 0 or 1. An important thing to notice here is that if the absolute value of r is not less than 1, then the series does not have a sum because it just keeps getting bigger and bigger and bigger, and you will denote that by saying no sum. So consider example 8. The fact that there's a big old infinity here is how you know that it's infinite. The fact that it looks exponential is how you know that it's geometric. So the first thing you want to do is you want to check, is the absolute value of r less than 1? Because that is the only way that this formula works. Because it is, you're good to go. That means you're allowed to find the sum. And notice it's not the sum of the first whatever terms because it's infinite, so it's just the sum. The numerator of your formula is what you get when you plug in the bottom number, again, regardless of whether it's 0 or 1. So 1/2 to the 0, that's 1. 1 times 5 is 5. 1 minus the common ratio is 1/2. Simplifies to be 5 over 1/2, which turns out to be a sum of 10. In number 7, again, once you see that infinity and once you have verified that it's geometric, you know that you are going to verify whether or not the absolute value of r is less than 1. So 0.2, we can see that it is. That means that to find the sum, you're going to have a fraction. The top is going to be what you get when you plug in that bottom number. So again, anything to the 0 is 1 times -10 is -10. 1 minus the common ratio of 0.2. That's going to give you -10 divided by 0.8. And if you simplify that with your calculator, turns out that the sum is -12.5. And again, as I mentioned earlier, for some reason, that 12.5 just seems to occur a lot in this section, but don't really think too much of it. Seems weird also that the formula for an infinite sequence would be easier than the finite one, but that's just the way that it is. Here in example 10, see the infinity. In order for this to work, you would have to verify that the absolute value of 6 is less than 1. Obviously, it is not. Because it is not, that means you are not able to find a sum for this problem. It just keeps getting bigger and bigger and bigger. 6 to the 0 plus 6 to the first plus 6 squared plus 6 cubed. That is not getting closer and closer to any particular value, which means that your answer would simply be no sum. Here in number 11, go ahead and take a look at the infinity. Go ahead and confirm that the absolute value of r is less than 1, which it is. Then go ahead and realize that the sum is equal to, here we're starting at 1. Again, remember, if you're going to infinity, it really matters not if you're starting at 0 or 1. So if you plug in 1, you get 0.6 to the 0, which is 1, times 4 is 4, over 1 minus 0.6. That's going to give you 4 over 0.4 for a final sum of 10. Hopefully you've been kind of keeping a running list of the formulas from throughout chapter 9. If you haven't, go back, be sure to add these to your list. Finally, a little bit of a reminder of the compound interest formula. This was back from chapter 3. So the final amount in your account is equal to the principal times 1 plus r over n, all to the nt. Remember, P is the initial investment. 1 stands for the fact that you're getting back 100% of your money. R is the interest rate expressed as a decimal. N is the number of times you compound per year, once a month, once a week, once a day. And then NT is the number of times you compound per year times the number of years. So to start us off, we're talking about a $50 investment at a 6% interest rate, compounded monthly, which is 12 times per year, over a total of 2 years. If you were to plug those values into the equation, and if you were to do a little bit of simplifying, that would give you 50 times 1 plus 0.06 to the 12th, all raised to the 24th. These are the types of problems we would have been doing back in chapter 3 to see how much money would be in your account after a certain amount of time if there was only one initial investment. The thing that's different here in chapter 9 is what if there is more than one investment? So let's assume that you deposit $50 on the first day of every month. So you don't have just one principal, you have a different principal every month. You're still assuming a 6% interest rate. You're still assuming that it's compounded monthly, and you're still talking about your balance at the end of 2 years. Please note, just for yourself, this is called an increasing annuity. So let's consider the first $50 that you put into your account. So the first $50 that you put in at the beginning of this time period is going to get interest for all 24 of the months. So in the formula, the exponent is 24. You could simplify 1 plus 0.06 divided by 12 to be 1.005, just to make this example a little bit easier. Let's talk about the deposit that you put in on the second month. That is going to get interest for 23 of those months, meaning that the only difference between the first term and the second term is the value of the exponent. Then consider the final deposit that you make. The final deposit you make is in the last month of your investment, which means it's only going to make interest for just 1 month. So when you simplify that, you're going to get 50 times 1.05 just to the first, which basically means that the exponent is not there. So why is this a sum? You're basically trying to add up the value of your deposit in the first month plus the value of your deposit in the second month, plus all of the values up to and including the deposit in the final month. So because of the fact that it's compound interest and it looks geometric, that's how we know that it's a geometric sequence, because it's exponential. The fact that you're only doing it for 24 deposits is what makes it finite. So we're going back to our first formula for the day. You're trying to find the sum of those 24 deposits. We're going to call A1 the value of the final deposit that you make, just because that's the simplest one. Then 1 from the formula minus R is 1.005. And again, we found that by simplifying the inside value of the exponent. Then divided by 1 minus 0.05, 1 minus 1.005. If you then go ahead and plug that very carefully into your calculator, you are going to get a final answer of $1,277.96.